Okay, welcome back everybody. So starting right on time, so great to have Aisling with us, Dr. Aisling Crowley, and she is presenting on behalf of, there's a team here, I know Dr. Cormac Quigley is here, Dr. Etain, Kiely, and Dr. Sheila Faherty. And we also have, this quite a wide team here, Dr. Jenny Ryan and Dr. Mossy Kiely. So fantastic, from the School of Science and Computing, and they're going to tell us all about data literacy. So thanks, Aisling.
Cool, thanks, Karina. So good afternoon, everyone. My name is Aisling Crowley, and I'm going to be presenting some of the work that we've conducted over the last year. This work involves introducing coding and data analytics to first-year students in the disciplines of maths, physics, chemistry, and biology. So data literacy is the ability to derive meaningful information from data in context, and coding, also known as computer programming, is essentially providing a set of instructions to a computer so a task or an action can be performed. So these skills are becoming massively important. So coding and data analytics or data literacy are becoming massively important, with a heightened attention on data around COVID-19, for example, as well as advances in the field of data analytics, as well as AI. So before I get into things, I suppose I just want you to introduce you to the team. So we have Dr. Etain Kiely who lectures in maths. We have Dr. Mossy Kiely, who lectures in physics. Dr. Jenny Ryan, who also lectures in physics. Sheila Faherty, who lectures in biology. Myself and Dr. Cormac Quigley, who lecture in chemistry. So I suppose the first thing we see is that we do have quite a nice interdisciplinary team, which is always lovely to have. We were also very lucky to get some pirate funding last year, and with this funding we were able to hire some student partners who were working as research assistants with us last year during the summer. So we had Cliona Fagan and David Dodge, who were final year physics and instrumentation students, and they were very instrumental in, I suppose, developing the initial codes and setups required for the practicals that we implemented in chemistry, physics and biology. So as I'm saying, this project encompasses not only chemistry, but physics, maths and biology. The main aims, I suppose, for the overall project were to introduce data analysis and coding of live data using microbits in first year disciplines of maths, chemistry, physics and biology. And what we also wanted to do was to break down the knowledge silos between these disciplines. And we wanted to address and try and challenge the assumptions around computational thinking and around data analytics. Now, the question that might be knocking about in your mind is the question that I had when this all first started, is what is a microbit? So this little guy here is your microbit. Okay, so it's a pocket-sized computer, and you can code it to be pretty much anything that you want. So today I've done a little code, so when I press the button B, I get a little music symbol popping up, and when I press A, I get a nifty little tune that comes out. So this is a very simple code, and it's just a little bit of fun. So to learn how to code this is actually quite straightforward. So there's a website called Make Code Editor, and when you go on there, you have a variety of codes that guide you through step by step. And you essentially learn to code in these things called blocks. And these blocks are very user-friendly. I could never code in my life. I can do a little bit now. It's really nice. And as your confidence grows with coding, you can actually translate these blocks into, I suppose, more complex programming languages like Python or like JavaScript. So it's really nice to build upon. The microbits themselves, they're fairly inexpensive, so about €25 will get you the microbit, the battery pack, the crocodile clips and everything else you need to get going. And if you don't want to do that, you can also use the simulator on the MakeCode website. So you can go on to the MakeCode website, build your code, and then you can run it on the simulator there. So it makes all of this very, very approachable, which is always nice. So today I'm going to be focusing specifically on the work we did and the chemistry element of this project. And you can see we have a few different steps. And I'm going to go through these in a bit more detail in the following slides. But before I do, I suppose we should talk about who's going to be in the chemistry lab with us. So in first year chemistry, we have about 300 students overall. We have, they're from these different courses, so we have common science, we have public health and nutrition, we have sports science, and we have medical science. I suppose a little caveat here and a little limitation is common science is the only, so common science consists of about 200 students. That's the only group that actually does take maths with Etain Kiely. So they were the main group that were actually being exposed to microbits and coding before coming into the lab with me. So that is a limitation, but we can discuss that a little bit later on. So what did they do when they were in maths with Etain? So Etain was kind of the first port of call where they got their introduction to coding and to microbits. So they were introduced to microbits, so Etain would have brought in something like this and showed them how that works, but they would have done a lot of their work on the simulator and MakeCode. And they would have done some work using maths journals on OneNote. So for example, one of the activities they would have done is they would have programmed their microbit to measure the temperature. And then they would have converted temperature in degrees Celsius to Fahrenheit. So this was their first introduction for a lot of them to coding and to the microbit. Now, while that was happening, we were actually developing a brand new chemistry lab practical, so we could actually incorporate the microbits, coding and data analytics. So the experiment we came up with basically focused around the students trying to determine the concentration of salt or sodium chloride in soy sauce using a conductivity probe and a microbit. So for students to do that, they prepared a series of sodium chloride standards of increasing concentration. They also had a dilute sample of soy sauce. They would have built a circuit which essentially consisted of their coded microbit, a resistor, their solution of their salt, and their probe. They would have used their microbit to measure the conductivity of each solution, and they would have plotted this data on Excel. And then using their equation on the line from their graph, they would have calculated the concentration of the soy sauce, or the salt in the soy sauce, and all going well, they should have gotten something around 150 to 200 grams per litre. So for that to happen, we have lots of different elements. So I'm going to give you a brief overview of the evolution of our conductivity probe, which you think would have been the most straightforward part and is the part that took us the longest to try and figure out. So these are my rough drawings of some of the initial things that we started with. So we had lots of different factors to consider. So do we use aluminium? Do we use copper? Do we use silver wire? Do we use plates or do we use wire itself? We have to consider electrochemistry, so how do these metals interact with our solutions of choice? We have to consider the reproducibility of the results, the linearity of results, lots of different things. And I suppose for this slide in particular, I really want to acknowledge the work done by Dr. Mossy Kiely and Dr. David McKay in physics, because they really did go above and beyond in developing a probe that actually worked for us. So eventually what we ended up with was a 3D printed sheet. So all of these were 3D printed in the physics department, and we ended up going with copper wire. And these were probes that worked really well for us. They were reproducible, they were reliable. What we also needed, obviously we have a conductivity probe, we have our probe now connected to our microbit, and our microbit needs to be coded to measure the conductivity. So just very briefly going through this, we have our on start, so when we power up our microbit, we should see a smiley face that tells us that the correct code is loaded onto our microbit. If we give it a shake, a diamond comes up, so we know that the battery is functioning properly. And the students, when they actually have their probe submerged in their solution, once they press A on their microbit, then they can start to measure what essentially is a voltage level. So everything is going on there, they can get their values, and again, they can plot these values later on. Now, the microbit itself does actually only measure voltage level, so the students would convert that mathematically themselves from voltage level to microsiemens, which is the unit of conductivity. Because we made all of this in-house, we thought it was important to do a bit of quality control and make sure things actually work as they should. So myself and Mossy gathered in the lab one evening, went through all 12 of them. It was great fun, as you can imagine. And obviously we plotted everything, so we can see that we did get great linearity for all of them. It meant when we went into the lab with the students, things were reliable, we felt confident in what we'd done. What we also did during this quality control session is we provide a familiarization session for the lecturers and the postgrads who are also going to be leading these labs, because this is new to us. So this gave the lecturers and the postgrads an opportunity to set up something themselves, ask any questions if they were unsure. What we also did was provide a lecturer's toolkit. So they were provided with a PDF document. It had sample results, it had troubleshooting, and also had some safety tips just to let them know. So again, trying to make everyone as comfortable as possible, introducing this new practical. Now for the students, and this is probably my favourite slide. So in chemistry, we always provide students with pre-lab activities. So before they came into the lab when they were going to be using microbits, they were provided with instructional videos, so they knew how to set up their circuit, how they could set up their experiment. And Etain Kiely actually designed an interactive tutorial that showed them how to actually code their microbit from beginning to end. You can't really see it here, but up on the top, it not only tells you what to do, it tells you why you're doing it. So it tells you the physics and the instrumentation behind the code, which is nice. Then the students completed a graded pre-lab quiz to kind of reaffirm and to obviously, I suppose, structure their learning there as well. Once students had gone into the lab, had obtained the results, they also complete post-lab activities. And we did that in the form of formula questions. Okay, so Cormac Quigley here designed this, so any questions for this, you go straight to him, you do not come to me. And so students were graded on this as well. Now, what we also wanted to do is obviously we wanted to gauge the students' feedback here. So we did have a feedback form. So this form was obviously completely voluntary, it's not graded. All the data collected was anonymous, and anyone who was under the age of 18 could not complete it. So overall, we had about 94 students who consented to their data being used for this research. And we just wanted to check in and see what their experience was before this, did they enjoy the lab, and so on. So we asked students, what was your previous experience with coding? 80% of students said they didn't have any, okay, which is fine. 7% of students acknowledged the work they'd done in maths with Etain Kiely. Etain finds it's very funny that, again, students didn't recognise what they had done in the lab with her. And this could be two things. So one, this might be that we actually have quite a high number of students from sports and sports science and medical science, and the groups that aren't in common science with Etain, which is fine. But it might also be acknowledging those knowledge silos that we talked about earlier, the inability of students to connect the work they've done in maths to the work they're doing in chemistry. So that might be something we need to address. Some students did have experience with microbits, Raspberry Pis and Arduinos in primary and secondary school, which again is just nice to know that this is kind of ticking away in the background. This slide here, there's quite a lot of information, but overall this is gauging the students' experience in the lab. And overall, this seems like they had quite a positive experience. So they enjoyed using the microbit, they found it easy to set up, they had a good understanding. So lots of positive things coming out of there. I think the main statement where we see a bit more of a spread is the very last question, is in I have an understanding of coding using MakeCode. So we have a few people who are saying, I don't, which is completely fine, because when you consider this is probably their first or second exposure to coding, I definitely wouldn't expect them to say, I'm fully confident in this now. So what we're hoping here is when they go into the biology lab and the physics lab afterwards, we are hoping to see more strongly agrees, more confidence with the coding aspect of it. We also, again, wanted to look at their ability to analyse data. So Mossy Kiely really came up with some phenomenographical studies, try to say that word. And so we essentially asked students, based on some of the work they've done in the lab, here's some kind of sample data. Do you think that using this data, you could accurately determine the concentrations of an unknown salt solution? So from the students' responses, about 44% or so gave an unexpected answer. And what I mean by that is an answer that deviates away from what we'd consider the conventionally correct answer. So this might be they got it partially correct, maybe they got the first part of a series of steps but didn't quite make it to the end. Others might have just been incorrect in saying, well, actually, no, we can't get a correct answer, when in reality we can. And then others might have just tried to apply different logic. So you see that they attempted to answer the question but just couldn't do it. We have internet clicker preferences here. I'm just going to say no. Then we had some students that just said they didn't know, they left it blank. And I suppose we had about 34% of students agree that concentration could be obtained, and they did elaborate. So they said, yes, we have 3 trials, we get an average, we can plot that data on a graph, we can solve an equation on the line, and we can solve, which is nice. Okay, so that's kind of our conventional, traditional expected answer. And we did have a small number of students who showed some other form of critical thinking. So if I quickly pop back to the slide, they were told that their unknown solution had an average value of 38. So what they did really was they went across, found values that were close to 38 and said, well, I'm going to assume that it should have a concentration of around 6 grams. So it's a different way to work it out. But again, I think it's something nice. Okay, it's a different way of thinking to reach a good answer, correct answer. We also asked students, how do we improve this lab? How do we make it better? So overall, lots of students, again, had no recommendations and or had a positive experience. We had some students asking for a bit more detail prior to the experiment. We had some students give practical feedback, which again I think is always really nice. So they want a rinsing step in between, so results aren't being skewed by previous readings. They want to go up in smaller increments. And then one student, and I just thought it was really nice, that they did a bit of self-reflection, which sometimes is a little bit lost in science. So they want to improve their petting skills, so they won't actually have a negative effect on their results, which again I think is positive. We did have 14% of students, and these encountered issues regarding the setup, so it was a bit finicky for them, a bit challenging. And this is a bit of feedback that I'm a bit torn by, because in the lab, this is the first time I've designed a practical from beginning to end, and of course I want the positive feedback. I want it to be seamless, but the reality is there a benefit to that? Okay, so for students to be challenged a little bit to encounter an issue that they have to problem solve, I think is a good thing. And it's something I suppose I'm thinking about a little bit more now going forward. We also reach out to our lecturers, so we're trying to get a fully rounded feedback on this. So we obtained feedback from the lecturers through in-person conversations as well as feedback form. And we did identify some limitations and suggestions for improvement. So as I mentioned earlier, one of our biggest limitations is essentially that not all of our students had experience with the microbits before entering the lab. We also found out our lab practical was just a little bit too short at the moment, so we need to kind of lengthen that. And obviously we would love, so the ideal would be that students come into the chemistry lab, they code the microbits there and then, rather than in their pre-lab activity. And then we can kind of implement it or integrate it there. But again, these are limitations for a reason. So the lack of PCs is the main reason we can't code in the chemistry lab. We have one PC, we have 16 students, it's not feasible. But looking forward, I suppose the things that we can change, we can improve. So how can we make sure that all groups are introduced to microbits? Well, we can integrate microbits and coding activities into the maths classes that are taken by medical science, by public health and by sports science. We might, some lecturers suggested maybe we run the physics microbit lab before chemistry, and I suppose that's because people often associate physics and microbits or physics and coding. They go more hand in hand. And we could also lead a chemistry tutorial in which we use the microbits and code there. So maybe that's something we could do in a computer lab before the lab itself. Another lecturer acknowledged that we could actually introduce a calibration step which will help improve the conversion from our voltage level to conductivity, which again I think will be a new skill for the students to have, and it will also again just extend the duration of our lab. And then finally, some lecturers kind of talked about introducing additional variables, so changing the resistor that we used and so on. So we did get a nice amount of feedback, and I do think it's stuff that's very implementable going forward. So going forward, what we need to do, so at this point, we have the chemistry labs have taken place, but we also have the biology and physics lab. So we need to now sit down and see, do we see any progress in students as they're going forward in terms of their data literacy, in terms of their competence with coding. Next year, we want to try and embed the coding in a chemistry tutorial, or if we could implement it in the lab, that would be the gold standard. We're going to introduce the calibration steps that are discussed. And on a slight tangent, we do want to introduce microbits kind of into the lab itself more passively, where we have environmental monitoring. And again, I do think there's something nice about students seeing the bare bones of the microbits and the circuits, rather than just seeing a TV screen with a number saying it is currently whatever temperature. I think there's something nice about them seeing what's going on behind that, the instrumentation. The conclusions here are quite short, and the reason for that is it's one very small piece of a very large project. And again, there's still a lot of analysis on these results to be done. So right now, as it stands, we have a brand new chemistry lab practical, which embeds coding, which embeds data analytics, embeds microbits, and we are hoping to run again next year. Overall, our students did seem to have a positive experience. They seem to be comfortable with the microbits, more so than we initially expected. And we're going to take the students and the lecturers' feedback and implement it to improve next year. So I'd like to thank you for your time, and if you do have any questions, I will try my best to answer them. So thank you.
Any questions for Cormac either?
Yes.
I have a question.
Yes.
So they're doing microbits now, but previous to this, what kind of practicals or labs were they doing, and how were they doing?
So in the chemistry labs themselves, they are very much chemistry focused. They are chemistry labs, so they do a lot of volumetric analysis, lots of synthesis. They do use instrumentation, and this is, I suppose, what we wanted to try and give a different perspective, because when they use instrumentation like UV spec, it's a plastic box with a screen and they push a button, they get an answer. There's no appreciation for the instrumentation, the coding or anything that goes on behind it. So they've essentially now designed or built their instrument, and we were hoping that could link in what they've done in physics, when they're building circuits. So that's why we want to do something like this as well. Yeah. I'm okay if no one else has questions, it's fine. Thank you, cheers.